Example 2 is multiplying rational expressions. What is the product here in simplest form? State any restrictions on the variable. So the very first thing we're going to do is we're going to write these in factored form. Numerator of our first one here. Multiply to x squared is x and x. Multiply to 6, subtract to 1. It's going to be 2 and 3. Since we subtracted, our signs are going to be different. Bigger number always gets a sign in the middle. X minus 5 is just x minus 5. X squared minus 25, again, that's a difference of squares. We need to multiply to 25 but subtract to 0. The only way we can do that is with a minus 5 and a plus 5. In our denominator, only way we multiply to x squared is x and x. Multiply to 3, add to 4, gives me 3 and 1. Since these signs are both plus, ours are going to be both plus. Now let's figure out any restrictions on our variable. X minus 5 can't be 0 because it's in a denominator. X plus 3 cannot be 0 because that would give us 0 in our denominator. And x plus 1 cannot be 0, again, because all those would give us division by 0, which means that x cannot equal, if we add 5, if we subtract 3, and if we subtract 1. Here's the restriction on our domain. Now, when we multiply fractions, we can multiply straight across. So everything in our numerator times itself, everything in our denominator times itself. It's one big fraction. So we can simplify between our two. Anything in the numerator divided by itself is 1. Anything in the numerator divided by itself is 1. Which leaves me with just x minus 2, x plus 5. Those are multiplied together over x plus 1. That color's kind of terrible, sorry. You can multiply that numerator out again if you want to, but you don't have to. We can leave it as the x minus 2, x plus 5, divided by x plus 1, as long as that is our restriction. And again, we can see the negative 1 from our final answer, but the two factors that canceled out, we can't. So we have to check our denominators all the time. We're going to try this one here. Again, our first step is to factor. So we're going to completely factor both of our fractions. In the first one, we just have an x, so we can't do factors of like x plus or x minus, but what I can do is factor out what's common. I can take out that 2. And I have 2 with x minus 4 left. X squared minus 16, again, is a difference of squares. X plus 4, x minus 4. Have to be the same number. Multiply to 16, subtract to 0, or 4 and 4. Times our numerator here of our second fraction. Multiply to 4, add to 5. It's going to be x plus 4, x plus 1. Same signs because we added both positive. In our denominator, we need to multiply to 16, add to 8. So we're going to do x plus 4, x plus 4. Okay, our domain restrictions, x plus 4 cannot equal 0. X minus 4 cannot equal 0. And then we have x plus 4 and x plus 4 again. We already have those listed. So x cannot equal plus or minus 4 if we subtract 4, if we add 4. Those are the restrictions on our domain. Now let's simplify here. Again, when we multiply fractions, we can multiply straight across into one big fraction. So I can simplify anything that's the exact same. Has to be the exact same. X plus 4 divided by x plus 4 is 1. Anything divided by itself is 1. This leaves me then with 2 times x plus 1 in my numerator. In my denominator, I have x plus 4 times x plus 4, which I'm just going to rewrite. Anything times itself means we can take it squared. So 2 times x plus 1 over x plus 4 squared, as long as x is not plus or minus 4. Same thing here with dividing rational expressions. With division, we end up multiplying by the reciprocal with fractions. So first thing I'm going to do is I'm just going to rewrite my fractions in simplified form. I'm going to write this numerator as negative x plus 2. And I do that because I always want to have that x positive. So what I'm going to do is I'm going to factor out a negative 1, x minus 2. I divide both pieces by negative 1, account for it out front, and now I have just x minus 2. Again, we always want that x to be positive. In my denominator, multiply to x squared is x and x, multiply to 1, add to 2, plus 1, divided by, in my numerator, x, and x is how we multiply to x squared. Multiply to 10, subtract to 3, 5 and 2. Different sign since we subtracted. Bigger number gets the sign in the middle, so the plus minus 2. And again, we have difference of squares here. X minus 1, x plus 1. So, because we have denominators, we need to check our restrictions. X plus 1 cannot equal 0. Same thing there. X minus 1 cannot equal 0, and I have x plus 1 repeated. So right now, I have x cannot equal plus or minus 1 when I solve those by either subtracting 1 or adding 1. When we divide fractions, we multiply by the reciprocal. So I keep my first fraction exactly the same. I do not change it at all. My second fraction, I take the bottom to the top, top to the bottom, the reciprocal. So I end up having x minus 1, x plus 1 in my numerator, and x plus 5, x minus 2 in my denominator. Now I have a new denominator, so I still need to check that for 0. X plus 5 cannot equal 0. X minus 2 cannot equal 0, which means in addition to the plus or minus 1, x cannot be negative 5 or 2. And those are all the restrictions on my variable. Now, since we're multiplying fractions again, we can multiply straight across. Anything divided by itself is 1. So I'm left with negative 1 times x minus 1 over x plus 1, x plus 5. If you wanted to, you could multiply those out. We don't have to. So we can leave it just like that, as long as x is not one of those 4 numbers. Quotient here, again, before we can simplify, we need to write it as factors. So we're going to start off with our numerator. Multiply to 4, add to 5, it's going to be plus 4 plus 1. In our denominator, in order to multiply to 12, subtract to 1, it's going to be 4 and 3. And the bigger number always gets a sign in the middle. When we subtract, the other number gets the opposite. Divided by difference of squares. The only way we multiply to 1, subtract to 0 is with a minus 1 and a plus 1. Here, I factor out what's common. I have a 2 and an x that I can take out of both terms, and I'm left with an x minus 3. So, every time that we have division, we need to check for restrictions. X plus 4 can't be 0 because it's in the denominator. The factor x plus 3 can't be 0. 2x can't be 0. And x minus 3 again can't be 0. And I already have that listed here. So I can subtract 4. I can make those not equals if you want. If it's easier for you to solve them with equals and then just know that they mean that they can't, that works too. Here we divide by 2 and I still get 0. Now, to get rid of our division, we switch to multiplication. We keep our first fraction exactly as it was. We never change our first fraction when we divide. The one that we take the reciprocal of is the second. Bottom goes to top, top goes to bottom. And again, every single time that we divide fractions, we multiply by the reciprocal. Now that we're multiplying, we can go straight across. And anything that's in the numerator and denominator, we can cancel out one set of. X plus 4 divided by itself is 1. X minus 3 divided by itself is 1. X plus 1 divided by itself is 1. We also have to make sure that we check our new denominators for restrictions. So in addition to this, x cannot be plus or minus 1. And you don't have to write them as plus or minus. It just saves a little bit of space. So here we have 5 different numbers that x can't be. Final answer is just going to be 2x over x minus 1. As long as x is not one of those numbers. So again, a lot of the same rules we had with fractions that didn't have variables in them or weren't factors with binomials, binomial variable factors. So quick recap here. Much of what's true about multiplying and dividing fractions can be used to multiply and divide rational expressions. We still multiply straight across and multiply by the reciprocal when we're dividing. A rational expression is in simplest form when its numerator and denominator are polynomials that have no common divisors. A rational function may have 0 or 1 horizontal or oblique asymptote and 0 or more vertical asymptotes. And again, remember, asymptotes are things that our graph is never going to cross or touch. Okay, vertical asymptotes, up and down, horizontal, left and right, and oblique are any of them that are at an angle. Functions such as f of x equals x plus a divided by x squared minus a squared, and g of x equals 1 over x minus a, as long as x is not plus or minus a, are equivalent. G of x is just a simplified form of f of x. I'm going to flip over to the assignment. I did change it a little bit for FBLA kids. Start at 27 there, not 26. Thanks.